Hello. So, we will continue our discussion on cloud computing. Today, we will discuss about some aspects of managing data in cloud, right. So, as we understand that in cloud, as we have discussed in our earlier lectures, that in cloud one of the major aspect is the data, because at the end of the day your data and even processes and applications are in somebody else's domain, right. So, they are in the is being executed at somewhere else which is beyond your direct control. So, it is virtually hosted in some virtual data, a virtual machine somewhere in the cloud. So, it becomes tricky to on the security point of view that we have discussed. Not only that, if you look at from the other point of view, from the cloud provider point of view, managing huge volume of data, keeping their replicas and making them queryable, and this becomes again a major issue. So, all our conventional relational or object oriented model may not directly fit into the thing, right. So long you are doing on a small instances like experimental cloud, experimental some database application or some small experimentations, then it is fine. But when you have a large scale thing where huge amount of read write going on, or the volume of data is much higher than the normal operations, then it is we need to look in a different way. These are the things which come into not only for the cloud, it was there little earlier also, like how this parallel database accesses, parallel database execution, read write execute operations can be done. So, those things become more prominent or a de facto mechanisms when you talk about in context of cloud. So, what we will try to do is more of a overview of how data can be managed in cloud, or what are the different strategies or schemes people or this ISPs follows, and it is not exactly the security point of view, it is more of a management data management point of view, right. Okay. So, we will talk about a little bit of relational database already known to you. Then what you want to do, that scalable databases or data services, like one of the couple of things are important. One is Google File System, Bigtable, and there is a map reduce parallel programming paradigm. Those are the things which comes in back to back when we are doing to the things. So, what we want to do whenever we are managing anything on a cloud platform, whether it is application or data, we want to make it scalable. Scalable in the sense that it should scale as the requirement goes up. So, scale up, scale down in a ubiquitous way, or minimum interference from the, or minimum human or management interference. So, that type of infrastructure we want to come up with, right. It is true for data also. So, these are primarily suitable for large volume of massively parallel text processing, right. That is one of the major thing, or it is suitable for environment say enterprise analytics, right. I have a if we want to do analytics on a distributed data stores, right. It may be a chain of a shopping or commercial stuff, or it may be a banking organization or any financial organization. Even it is something to do with large volume of other type of data, like it may be a meteorological data, it may be climatological data, something which need to be churned or has a distributed things, I need to do some parallel processing down the line, where the actual effect comes into play. If you have a simple database with a simple instance, then you may not have gone to cloud for that, right. So, it is maybe a simple system, or you buy a very a VM and work on it. Then the actual effect of cloud things are actual advantages of cloud you are not taking out. So, we will see that similar to big table models, there are Google App Engines data store or Amazon SimpleDB, which are different providers provide in different flavor, but the basic philosophy are same. So, if we quickly look at the relational database, which is known to all of you or most of you, users application programs interact with RDBMS through SQL, right. So, it is the structured query language or SQL by which we interact with the user programs, etc. So, there is a relational database management parser which transform queries into memory and disk level operations and optimize the execution time. So, in any query we need to optimize the execution time of the query, right. So, if it is a large database, like whether you do project before select, join before or after select, that makes a lot of difference. Though the query may be same, the query output will be same, but the execution time may vary to a great extent, right. Like I have a huge two databases, like R1, say relational databases R1, R2, and I do some projection or selection of some of the things, right. I select A1, A2 and then do the join, right. Whether I do the join before or after makes the things, like suppose if I do the select on R1, the number of tuples come down from 1,000,000 to say few thousands. Similarly, for R2, if I do a select on that, right. So, then joining is much less costlier. So, whether you do the join first or etc., that becomes the things. That is a database optimization problem, nothing to do specifically for cloud, but relational database allows you to optimize those things. Disk space management layer, this is another property, the stored data records on pages of contiguous memory blocks, so that the disk movement is minimized. Pages are fetched from the disk into memory as requested using prefetching and page replacement policies. So, this is another aspects of the things, like one is looking at that proper, making it more efficient in the query processing, other aspect is make it more efficient in storage terms of things, like nearby things. If the query requires some 5 tables, if they are nearby stored, then the access rate is high. So, database file system layer. So, previously we have seen RDBM parser, then disk space management layer, then database file system layer. So, it is independent of OS file system, it is a separate file system. So, it is in order to have full control on retaining or realizing the page in the memory. Files used by the DB or database may span multiple disks to handle large storages, right. So, in other sense, like if I dependent on the operating system for fetch all those things, then it is fine when your again database load is less. If it is pretty large, then the number of hop you take, it becomes costly. So, what you need to do, we need to do directly interact at the much lower level with the hardware or the available resources, and that exactly this database file system layer tries to emulate. Uses parallel IO, like we have heard about RAID disk, RAID 1, RAID 2, RAID 5, RAID 6E and type of things, arrays or multiple clusters. So, which keeps a redundancy into the thing. So, the your this failure downtime is much less. So, that means it is basically full failure proof implementation of the database. So, usually the database storage as row oriented, that is you have tuples and it is a set of row of the same schema, optimal for write oriented operation, the transaction processing applications, relational records stored in contiguous disk pages, access through indexes, primary key on specific columns. B+T is one of the favorite storage mechanisms for this sort of thing. Column oriented, efficient for data warehouse workloads, right. So, those who have gone through data warehouses. So, it is a high dimensional data, huge volume of data and being collected and populated by different things. So, it is not a, it is more of a warehouse rather than a simple database. So, this column oriented storage are more suitable for data warehouse type of loads, aggregate of measures where rather than individual data, it is more of the analysis or analytics come into play. So, it is aggregation of measure columns need to be performed based on the values of the dimension columns. So, we are not going to the data warehouse. So, it has a different dimension tables and type of things, and we need to, the operations are more aggregate operations, right. We want to do some sort of analysis and type of things. So, projection of a table is stored on stored on a dimension table, dimension values in case of a column oriented, require multiple join indexes if different projection are to be indexed in a sorted order, right. So, it is, if it is a different things, because the organization may have different views for different type of data and need to be stored in that fashion. So, data storage techniques, as we have seen, it is B plus tree or join indexes. So, if it is so one is row oriented, other one is column oriented. So, this is row oriented data and this is column oriented data, and we need to have a join index which allows this data to be linked to one another. So, all this you will get in any standard database book or any standard literature. Primarily, as we have mentioned, we are following that Gautam Shroff Enterprise Cloud Computing book for this particular thing. So, that is why you have mentioned, but this is a very standard operation and you can get in any standard books. So, if you look at the parallel database architectures, so it is broadly divided into three aspects. One is shared memory, one is shared nothing, another is shared disk, right. So, I will just see the picture first, then come back. So, this is a typical structure of the shared memory, right. So, these processors, different processors share the memory. Here it is a shared disk. So, different processors share the disk, and here we have shared nothing. So, individual processor has individual disk. So, in case of a shared memory suitable for servers with multiple CPUs. So, if there are multiple CPUs, memory address space is shared and managed by SMP operating systems, like the memory address space is shared among these SMPs, and schedule processes in parallel exploiting the processors. So, it schedules one things. So, that means I have a shared memory space and I basically do a execution in a parallel mode. So, on the extreme other end is the shared nothing. So, cluster independent servers with each of its having own disk space and connected by a network. So, with a backbone high speed network, every server shares its own disk space and then do the rest of the execution. And if you look at that, in between the thing is the shared disk, like it is a hybrid architecture. So, to say independent server cluster storage through high speed network, that can be NAS or SAN, and clusters are connected to storage data via standard Ethernet, fiber, etc. What we have shown here. So, it is a shared storage and these different processor access this. So, based on your application type of parallelisms you need, we can go for any of this structure. So, here we see that it is more more efficient if the memory things are more compact, where in the other end if the processors are individually working on separate data sets and they are not machining to share, then this could have been an advantage. So, if we look at the advantages of parallel DB of relational database, if we do not want to put that, what are the features of relational parallel database structures which is more advantageous for parallel this sort of operations than the relational database. Efficient execution of XML query by exploiting multiple processors. For shared nothing architecture, tables are partitioned and distributed across processing table, right. So, if it is so happen that I can partition the table and every data content in the table can be executed parallelly. They can be distributed in the different disks and the processor can work. That totally depends on your what is your working mechanisms out there. So, SQL optimizer handle these distributed joins. So, whenever we need to do some join, then we need to fall on the distribute your SQL optimizer. So, distributed two phase commit locking for transaction isolation between the processors. So, these are the some of the features. Fault tolerant, like system failures handled by transferring control to standby systems. So, I can have different standby system or some with some protocol or some policy, and then if there is a failure, then I can shift that particular execution to a some of the standby system. So, that is possible in this side of things, and restoring computation for data, those these are the things which are more required for data warehouse type of applications. So, there are examples of databases capable of handling parallel processing. Traditional transaction processing things are Oracle, DB2, SQL Server. Data warehouse application are some of the Vertica, Teradata, Netezza. These are the some of the things which are more of a data warehouse type of database. Now, with this background or with these things in our store, what we say, we look at that cloud file system. Now, as we understand, it will not go something become totally, we cannot throw the whole thing out of the thing and start doing something new, because this database has grown for years. They are fault tolerant, they are efficient, we have RAIDs and type of things. So, we need to exploit some of the things and put some more philosophy of which behind the cloud. So, one of the predominant thing is cloud file Google File System or GFS, and back to back we have a open source stuff called HDFS, Hadoop Distributed File System. So, which is what we say some one-to-one mechanisms with Google File System. So, Google File System designed to manage relatively large files using a very large distributed clusters of commodity servers connected by a high speed things. So, it is whether GFS or HDFS, they are enabled to work on very large data files which are distributed over this commodity servers. Typically some of the things are Linux servers which are which are interconnected through a very high speed LAN. So, they can handle failure even during read write of individual files, right. During the read write operation, if there is a failure, it can handle. Fault tolerant, it is definitely a necessity. So, if we have any simple system term that P of system failure, probability of system failure is 1 minus 1 by 1 minus 1 minus probability of component failure to the power n. So, for if the n is pretty large, then you can say that we can go for a, that is the risk of this failure is minimum. So, supports parallel reads, writes, appends, multiple simultaneous client program. So, it is parallel read, parallel write and update by the client program. And we have HDFS, that is Hadoop Distributed File System, which is open source implementation of GFS architecture available on Amazon EC2 cloud platform. So, we have HDFS which is there. So, if we have a big picture, so that how a typical GFS are there. So, there are some of the components are, that is master or the name nodes, master node in GFS or name nodes is in HDFS, and there are client applications, and we have different chunk server in case of GFS and data nodes in the case of HDFS in a typical cloud environment. So, single master controls the namespace. So, logically a single master is there which controls the namespace. So, namespace is important because it gives us that how data are stored, how data can be referred. It is more of a a metadata sort of information which is controlled by the master. Large files are broken into chunks in case of a GFS and block what we called in case of a HDFS. Stored on commodity server, typically Linux servers called chunk servers in GFS and data nodes in HDFS. So, replicated 3 times on different physical rack network segment. So, this chunk. So, what we have? We have the GFS or HDFS in the things. Below that we are having a chunk servers which are basically Linux servers, chunk server or data nodes in the things which are the main custodian of the data, and they are every data DI is replicated on different 3 times, at least 3 times on different physical rack and network segments. So, if we look at the read operation in GFS, so client program sends a full path and offset of a file to the master, right, where it wants to read, or name node in case of HDFS. So, we will refer the GFS master node and which is back to back when it is referred to the name node in HDFS. Master replies on metadata for one of the replicas of the chunk where this data is found, right. Client caches the metadata for faster access, right. It reads the data from the designated chunk server. So, master from the master it gets the client gets the metadata, and from there it basically access this chunk server. So, for read operation any of this chunk server or replicated chunk server will do. Where write append operation in GFS is little tricky. Client program sends a full path of a file to the master GFS on name node HDFS, right. The master replies on the metadata for all replicas of the chunks where the data is found. The client sends data to be appended into the all chunk servers. Chunk server acknowledges the receipt of the data, master designate one of the chunk server as primary. The primary chunk server appends his copy of the data into the chunk by choosing an offset, right. So, that it does. Appending can also be done beyond end of file to account for the multiple simultaneous writes. So, this is a pretty interesting thing, that even if you can append end of EOF beyond EOF, because there are simultaneous writers which are writing and it basically consolidated at a later stage. Sends the offset to the replica. If all replica do not succeed in writing in the designated offset, the client retries, right. So, the all offset. So, idea is that whenever I am looking for a data, I need to know that for all the 3 replicas it should be at the same offset ideally. So, that the read process there is no delay in that things, because once it calculates it directly access the other chunks on that offset, right. So, fault tolerant in Google file system, the master maintains regular communication with the chunk server, what we say heartbeat messages, sort of a are you alive type of thing. And in case of a failure, chunk server metadata is updated to reflect failure. For failure of primary chunk server, the master assigns a new primary. Clients occasionally will try to this failed chunk server, update their metadata from the master and retry. So, in case of a failure, the chunk server metadata is updated reflect the failure. So, the chunk server metadata says that there is a failure. So, the next time you do not allocate or like that, and for failure of the primary chunk server itself, the master assigns a new primary. So, it assigns a new primary to work on the thing, and update the clients occasionally will try to this failed chunk server, because it will be flagged, right. Now, another related stuff is big data or related concept is big data, distributed structure storage file system built on GFS, right. So, it is a structured distributed structure storage file system, it is built on GFS, right. So, data is accessed by row key, column key, timestamp. So, if you look at, so it is a multiple instances are stored. So, there is a time key, column key, and of course, a row key which says that where the data is there. So, in big table each column can store arbitrary name value pair in the form of column, family and label, right. So, here if you can see that these are column families and it is labeled and they store a name value pair. Set of possible column families of a table is fixed when it is created. So, which are the different column families will be there. So, that is somewhat fixed. Labels within a column family can be created dynamically and at any time. So, I can recreate the or create the table. Each big table cell, row and column can store multiple versions of the data in decreasing order of the timestamp. So, that means, it is the chronology is maintained in that fashion. So, it is multiple versions are stored in a decreasing timestamp. So, again we see these things. So, there are different tables, there are different tablets which are referred to this table and it is a hierarchical structure, and we have a master server. It is primarily a registry or a metadata repository. So, each table in big data is split into ranges called tablets. Each table is managed by tablet server. So, it stores each column family for a given row range in a separate distributed file called SS table. So, this type of management goes into play. So, that the my access rate, end of the day the access rate or will be pretty high. So, a single metadata table is maintained by the metadata server. The metadata itself can be very large. So, that metadata while storing this itself can be very large. In that case, it is again broken down into split into different tablets. A root tablet points to the other metadata tablets. So, if the metadata repository is pretty large, it is again broken down into different tablets, and there is a root tablet which coordinates with the your metadata these tablets and want to emulate or realize that metadata services. Supports large parallel reads and inserts even simultaneously on the same table. Insertion done in sorted fashion requires more work than the simple append, right. This is true for other databases also, because once you insert, it is basically you need to push the data aside and create a insertion point, whereas in case of a append you are putting data at the end of the that storage or data or the tables. So, Dynamo it is developed by Amazon, that supports large volume of concurrent updates, each of which can be small in size. Different from big table, supports bulk read and writes, right, in this. So, data model for Dynamo, it is a simple key value pair, well suited for web based e-commerce type of applications and not dependent on underlying distributed file systems, right. For failure handling, conflict resolution, etc., they do it themselves. So, this is typical architecture of the Dynamo, where there are several virtual nodes and different physical nodes, and their logical connectivities are shown. So, if we look at the Dynamo architecture, so it is a key value pair with arbitrary value key value pair with arbitrary arrays of bytes, like. So, it uses MD5, generates a 128 bit hash table, hash value. So, it basically try to map that where virtual node it will be mapping to by using this hash function. Range of this hash function is mapped to as we are discussing that set of virtual nodes arranged in a ring type of things. The object is replicated as a primary virtual node as well as n minus 1 additional virtual nodes. The n is the number of physical nodes. So, that any the object is replicated into the things. Each physical node server manages a number of virtual node at a distributed position on the ring. So, if you look at that this physical node server, they are basically linked with this virtual node server. Dynamo architecture, prime load balancing for transient failure, network partition, this can handle. Write request on object that executed at one of its virtual nodes, right. Forward all the requests to all other nodes. So, it is executed one of the virtual node and send all other nodes which have a replicas of the object. So, that means, if I am a object, if it is replicated into another n minus 1 node. So, one is updated, rest are being communicated. So, there is a quorum protocol that maintains eventual consistency of the replicas when a large number of concurrent reads and writes going on. So, this quorum tries to find out that which are the minimum level of replica will be there to handle this large read write operation. So, next we are having this Dynamo distributed object version. Write creates a new version of the objects in his local timestamp created. There are algo for column consistency. So, read operation R, write operation W. So, read plus write operation should be greater than n if the system is quorum consistent. There are overheads which will be coming up. There is the efficient write, large number of replicas are to be read, and if it is for efficient read, large number of replicas need to be written. So, these are the two things which are there. So, it is implemented by different storage engines at node level, Berkeley DB used by Amazon, and can be implemented to using MySQL and etc. Another the final concept what we are having is the data store. Google and Amazon offer simple traditional key value pair database stores, right. Google App Engine's data store, in case of Amazon what we say simple DB. All entities objects in the data store reside in one big table, right. Data store exploit column oriented storage, right. Data store as stored data as a column family. So, unlike our relational traditional thing is a more of a row family or tuple base, it is called column family. So, there are several advantages or several features or characteristics, like multiple index tables are used to support efficient querying. Big table horizontally partitioned called sharded and across the disk, whereas stored lexicographically in the key values of the thing. Beside lexicographic sorting of the data enables, there is a execution of prefix and range queries on key values. Entities are grouped for transactional purpose, because if when we are having transactions, so that is a set of entities which are accessed in a more frequent way, and index table to support varieties of queries. So, we can have different indexes or different type of queries. So, it is not, we should understand, it is not a simple a database, it is a large database. So, in order to do that, I cannot churn the whole database. So, need to slice them appropriately, so that based on the different queries, it can be executed more efficiently. And there are few more properties, like automatically it creates indexes, single property index, or there is a kind index, supports efficient lookup queries of form select all type of things. They are configurable in indexes, and there is a query execution indexes with highest selectivity is chosen, right. So, it is when we do the query execution. So, with this we will stop our discussion here. So, what we tried to discuss oversee is the different aspects. We have the notion of our traditional databases, which is established, fault tolerant, efficient, and there are different mechanisms to do that. So, we have also already these parallel execution things, and it is present. So, when we deal with a large volume of data in the cloud which are likely to be there, then what are the different aspects we need to look at. So, we may not be able to follow this column oriented or tuple oriented relational database, we need to row oriented database, we need to for column oriented database, and there are different file system like GFS, HDFS, and over that this data store, Dynamo, and your simple DB and those things which are being implemented by various cloud service providers, CSPs, for efficient storage, access, and read write execution of very large databases. Thank you.